Go back 3.8 billion years, and you'd recognize the solar system immediately. The Sun is there, Earth is there, Mars, Jupiter, Saturn, all moving through orbits that look strangely familiar. But look closer. Something is wrong. The Sun doesn't look the same. The surfaces of the planets don't look the same. Even Earth, the world you're standing on, is almost unrecognizable. And across the solar system, events are unfolding that will determine what these worlds eventually become. Some will lose what they once had. Others will preserve scars for billions of years. And on at least one world, something is happening that will eventually change the story of the solar system completely. This isn't the birth of the planets. That happened hundreds of millions of years earlier. This is something stranger. A solar system that already existed, but hadn't yet become the one we know today. So let's go back 3.8 billion years and see what was really here. The Sun is the first clue to how different this world was. 3.8 billion years ago, it was roughly 25% fainter than it is today. Its position hadn't changed, but its luminosity was only about 3/4 of what it is today. With a sun that dim, Earth's surface should have been far colder than the geological record suggests. Yet the rocks tell a different story. Rock formations from that era, and even slightly earlier, show clear signs of liquid water. Not ice, not vapor. Liquid, sitting on the surface, doing what liquid water does. Something was keeping that heat trapped that shouldn't have been keeping it trapped at all. And that mismatch has a name: the faint young sun paradox. The leading explanation is a thicker blanket of greenhouse gases, methane, and carbon dioxide most likely, doing the job the sun couldn't. That explanation isn't without its own complications. Estimates of how much carbon dioxide the early atmosphere would have needed to keep oceans liquid run higher than some of the geological evidence from that period seems to support. Some researchers have proposed additional factors: an early Earth with fewer clouds reflecting sunlight back into space, or an atmosphere thick enough in nitrogen to trap heat more efficiently even without extra carbon dioxide. Others point to methane produced by early microbial life itself as a possible extra contributor. No single idea fully closes the gap on its own. Most likely, several factors were working together, each covering part of the distance between a fainter sun and a planet that somehow never froze. Which means the air alone was already fighting to keep this planet from freezing over. But the sun wasn't the only part of the system that looked unfamiliar. Look up on that early Earth, and the moon isn't where you'd expect it either. It's closer, considerably closer. Today, the moon is receding by about 3.8 centimeters each year, although that rate has changed enormously over geological time. We know that 3.8 billion years ago, the moon was substantially closer, hanging larger and brighter in a sky that looked nothing like the one you're used to. A closer moon would have produced stronger tidal effects on oceans that hadn't yet settled into anything resembling the coastlines you're used to, and the day itself doesn't match either. Earth was spinning faster then, so its day was shorter than today's 24 hours. The moon's unusual closeness traces back to how it may have formed in the first place. One widely supported idea holds that a Mars-sized body collided with the young Earth, and the debris thrown into orbit gradually gathered into the moon we know today, already spinning close to its new parent world. If that happened, the earliest moon would have hung remarkably near Earth, long before the slow tug-of-war with the tides began pushing it outward year after year for billions of years since. The same tidal exchange that separates them today was, in that early period, still very new, still transferring far more momentum with each orbit than it does now. A closer moon, a shorter day, a weaker sun, held in check by a thicker atmosphere. None of these changes explains the violence yet, but together, they tell us something important. Earth wasn't simply an older version of today's world. Its entire environment was still different, and the moon was about to give us a much more direct clue. Then the moon's rocks reveal something much harder to explain. The Apollo missions brought pieces of the moon home, and the ages locked inside some of those rocks told a stranger story than anyone expected. A cluster of impact melt samples, several of them dating to a window somewhere around 3.8 to 4.1 billion years ago. To the scientists studying them, it looked like evidence of a sudden spike in bombardment, arriving long after the leftover rubble from planet formation was expected to be gone. That idea became known as the Late Heavy Bombardment, and for decades it was treated as one of the more dramatic chapters in the solar system's early history. But the closer researchers looked at the sample record, the messier that picture got. Some of those melt ages may not represent one sudden catastrophe at all. They could be the scars of a single enormous impact basin, sampled repeatedly by missions that kept landing near the same region. The question was never fully settled. Some researchers still argue for a genuine late spike. Others think the moon's record has simply been misread. Part of the challenge is where the samples came from. Apollo missions landed at only a handful of locations, most of them near a small number of enormous impact basins, including Imbrium and Orientale. A single giant impact can melt and reset the age of rock across a huge area, and later, smaller impacts can excavate and redistribute that same melted material. So, some scientists argue that Apollo astronauts may have unknowingly sampled the debris of one or two colossal events over and over, creating the appearance of a widespread spike in bombardment, when the true picture may have been quieter and more gradual. Newer missions and improved dating techniques are still trying to settle the question. Either way, it leaves the same unresolved question standing. Had the solar system actually reached a lasting equilibrium by then, only to suffer one violent relapse? Or had it never really finished being dangerous in the first place? One major class of explanations points in the same direction, toward the giant planets and whatever they may have been doing while nothing else was around to notice. And the possible mechanism points outward. One model, researchers call it the NICE model, proposes that the giant planets weren't always where they are now. Jupiter and Saturn in this picture started out closer together, still surrounded by the wide disk of icy debris left over from the solar system's birth. Then, in some versions of this model, their orbital relationship shifted. Simulations suggest Jupiter and Saturn could have settled into a resonance, Saturn completing one lap for every two of Jupiter's, and that single alignment may have been enough to destabilize everything nearby. This is one family of models offering a possible mechanism, not a confirmed explanation for what happened 3.8 billion years ago specifically. The disturbance could have propagated outward from there. Neptune and Uranus may then have been pushed into wider orbits, moving through debris that had remained relatively quiet since the solar system's formation. Some of it scattered further out, seeding what's now the Kuiper Belt. Some of it, in these simulations, went the other way, inward, toward the Sun, straight through the orbits of the inner planets. There's other evidence that points towards some version of this planetary rearrangement. Jupiter's orbit contains two clusters of asteroids, the Trojans, trapped in stable points ahead of and behind the planet, and their orbits carry signatures that are easier to explain if Jupiter's position shifted at some point after they were captured. The Kuiper Belt itself is oddly structured, with populations of icy bodies sorted into patterns that many researchers think only make sense if Neptune swept through the region on its way outward. None of this proves exactly when the shift happened, or that it lines up precisely with the bombardment on the Moon, but it does suggest the giant planets did not stay put toward a Moon and an Earth that may have long since stopped expecting to be hit. If something like this occurred, the chaos wasn't a random leftover of formation still winding down. It would have been triggered by planets that already occupied mature orbital configurations, doing something that reopened the entire inner solar system to bombardment, and Earth would have been exposed to that same chaotic environment. But unlike the Moon, Earth has spent billions of years erasing its oldest surface through erosion, volcanism, and plate tectonics, burying whatever record of that bombardment it once held. The Moon simply never got the chance to forget. A different sun, a different moon, possibly a solar system torn back, open by its own giant planets. And somewhere inside all of that, the most surprising piece of evidence isn't another crater, it's something far smaller. In Isua, Greenland, rock formations dated to roughly 3.7 to 3.8 billion years old contain graphite with a specific carbon signature, a ratio that, on Earth, is often produced by biological processes, though similar patterns can also arise from non-biological chemistry. Some researchers argue it's among the oldest possible evidence of life itself. Others remain unconvinced. Isua isn't the only place holding on to clues this old. In northern Canada, rock formations in the Nuvvuagittuq Greenstone Belt have been dated by some researchers to nearly 4.3 billion years, and they too contain structures some argue could be linked to ancient microbial activity, though that claim is even more contested than the Isua evidence. Slightly younger rocks in Western Australia, dated to around 3.5 billion years, preserve layered structures called stromatolites, built up by microbial mats and considered some of the most widely accepted early evidence of life. Taken together, these scattered, imperfect traces suggest that whatever was happening on Earth during this violent stretch, life was not simply waiting on the sidelines for it to end. Those impacts could have devastated environments on the surface, but impacts can also deliver water-bearing material and organic compounds while radically changing the chemistry of the surface itself. Whether that made Earth's early environment more hostile to life, more favorable to it, or simply different, we still don't know. Violence and the first hints of biology occupying roughly the same broad stretch of geological time. Whether one made room for the other, or the two simply happened to overlap, is a question the evidence still can't answer. So the real anomaly was never that Earth got hit 3.8 billion years ago. Young planets get hit. That part isn't strange. By then, the solar system was no longer supposed to look like the debris-filled environment of its infancy. Yet the evidence suggests some of that early violence may have returned, possibly driven by changes in the orbits of the giant planets themselves. And underneath that second wave of violence, on a planet kept liquid by an atmosphere doing a job its own star couldn't, life itself may already have been present, not waiting for the chaos to end, but already there while it was still happening. Perhaps life didn't need the solar system to become completely quiet before it could begin. Or perhaps the two events had nothing to do with each other. 3.8 billion years later, we still can't tell from the scars alone.